What up, YouTube?
So in this lab, we talk about fluids. A fluid is a substance that flows, such as liquid or gas. In this lab, we explore the properties of fluids by looking at Archimedes' principle, which is the buoyant force is equal to the density of water times gravity times the volume of the object, and the volume of the water displaced is equal to the volume of the object. We also use Bernoulli's equation, which is derived from the fact that energy is conserved in this system. So we have kinetic energy here represented by 1/2 rho v1 squared plus potential energy, which is rho times g times y1, and then we have the pressure of the system, which is representative of work. In this part of the lab, we measured the mass of an aluminum object. In order to do that, we filled the graduated cylinder with a known amount of water, and then we placed the cylinder in the water and took another measurement. To calculate the mass, we had to take the difference between those volumes in order to find the volume of the object. We knew the density based on the table in the back of the book, so we could plug it into this equation here. So to do the calculations for this procedure, we used the density equation, where the density of aluminum equals the mass of aluminum over the volume of aluminum. In order to get our volume of the object, we took the measurement of the final volume, and we decided that this had an error of plus or minus 5 milliliters, and we subtracted the initial volume from the final to get 120 milliliters, which is equal to 120 centimeters cubed. From there, we were able to convert to meters cubed. We got 1.2 times 10 to the minus 4 meters cubed. We were able to take our value that we retrieved from the back of the textbook, 2,700 kilograms per meters cubed, and plug that into the density equation to solve for mass. We got our mass to be around 0.324 kilograms. So in order to propagate our error, we took the error that we associated with the volume and converted it to meters cubed. We then multiplied our density from the back of the book, and because there's no error associated with this value, we were able to just multiply it out to the volume that we got and the volume associated with our error in order to get the approximated error of mass.
So in this procedure, we're looking for the density of a copper object using buoyancy. And so we're going to be using this set of equations here. So first, we're going to use the sum of forces because, so we're going to have the object, it's going to be hung with a thread, and we're going to submerge it into water, and we'll compare its mass to the apparent mass that it will have once it's submerged in the water. And then we'll find the buoyancy using the sum of forces, and then we'll use the buoyancy to find the mass of the water, to then find how much water was displaced, and then from that we can deduce that the same amount of water that's displaced is the amount of volume in the object. And then that way we can use the mass of the object and the volume of the object to find the density. So this is how it went down. First we measured the mass of the object using a triple beam balance, and we got a 64.79 times 10 to the negative 3 kilograms. We hung it by a hook on the triple beam balance and submerged it into water and got the apparent mass then. That is this number here, 57.70 10 to the negative third. And then we used the sum of forces, which is pictured here, to find the tension. So because the tension is pointing up and the buoyancy force is pointing up, those are positive. And then we have a minus Fg because it's pointing down. And then here it is with all the values plugged in with 9.8 for G. And then so we get this. So when we get this buoyancy force, calculate the mass of the water displaced, because we know that the mass of the water times g is the buoyancy force. So that's this number right here. And then we can plug that into the density equation, and we've rearranged it here to be volume equals mass over density. And this is the density of water. Here is the mass of the water that we just found that is displaced. That gives us the volume of the water displaced there. And then because we know the volume of the water displaced is the same as the volume of the object, we can use this equation here, density equals mass over volume, to find the density of the object, and that gives us our density. Are we doing it horizontally?
Is that even a question? Sorry. For procedure 3, we wanted to find the velocity of the water leaving a container, and we did so using Bernoulli's equation, which is based on the conservation of energy, where you have a kinetic energy term, a potential energy term, and a work term, and it's equal to the final versions of those. So, our apparatus essentially looked like this. We had this container filled with water. We had this little hole here where the water could shoot out and drain into the sink. The things that we measured here was the distance between the top of the water and this little hole here where this thing was sitting. And then we also measured the distance from the hole here in the X direction to where the water ended up shooting. And for those values, we got this distance here to be 3.7 times 10 to the minus 2 meters. This distance here to be 2.9 times 10 to the minus 2 meters. And then the distance that the water shot out in the X direction to be 5.7 times 10 to the minus 2 meters. And one important thing to note here is that atmospheric pressure exerting force here, and you have atmospheric pressure here. So we were able to calculate a theoretical velocity of this water using this equation here, the square root of 2 times g times our y initial. Using that and plugging in our values, we got 1.137 meters per second, and then we were able to calculate the theoretical kinetic energy that this water would have leaving the hole, which we got 646.4 joules. And then using kinematic equations, we were able to solve for our experimental velocity. The velocity squared in the y direction, final, is equal to the velocity initial squared plus 2 times the acceleration plus y. So we calculated 0.754 meters per second for the y direction. We were able to find the amount of time that it took for this to happen using this equation, where velocity final in the y direction is equal to velocity initial plus a delta t, and we got that to be 7.69 times 10 to the minus 2. And then we could calculate our velocity in the x direction using the delta x is equal to velocity initial in the x direction times delta t plus 1/2 a delta t squared, which this term is 0 because there is no acceleration in the x direction. And we got our velocity in the x direction to be 0.741 meters per second. And then using that, we could find our experimental velocity using our good friend Pythagorean theorem. And we calculated that to be 1.057 meters per second. And using that value, we got a kinetic energy to be 558.6 joules. And calculating the percent energy loss, we got 13.6% loss.
In the first part of this lab, we used the density to creatively find an unknown mass. This would be useful if you were stuck on a desert island and for some reason you wanted to know the mass of a coconut.
In the second procedure, we use Archimedes' principle to find the density of an object by measuring the buoyancy and the apparent mass.
So using Bernoulli's equation, we can predict the velocity of a fluid exiting any sort of opening. So I guess that could be useful in that we can find out how fast water is coming out of a hose or something.
Thanks for watching. Don't forget to hit that like button. Leave your favorite animal in the comments below. Subscribe, share this video to all your friends.
New videos every Wednesday.
Follow me on Twitter at physicsnerd367.
And don't forget to follow me on Instagram, like all my pictures, and yeah, that's about it. You can delete that entire section.
No.